Good afternoon, everyone. This is Collect First, Ask Questions Later. And this talk tells the story of how we at Fleet use the standard library tools to improve our ability to resolve problems in our Go server. We also love the tools in Go. That's a big part of the reason why we use it. And we looked at the idea of expanding those tools, packaging all of them up, and making it easier to do these things. So here's the joke. A friend told me to shoot first and ask questions later. I was going to ask him why, but I had to shoot him first. This talk will be peppered with, hopefully, helpful advice. Some of what we'll be discussing is quite specific to Fleet's use cases and the infrastructure that we use, the style of deployment that we use. But some of it also generalizes, and when it does, I'll try to point that out with slides that look like this. So, as you heard, I'm Zach Wasserman, co-founder, CTO of Fleet. I'm a co-creator of OS Query, and I also serve on the steering committee for OS Query. And I've been writing Go since 2016. Fleet is a server that manages OS Query, sometimes on hundreds of thousands of devices. It's open core, so a lot of the code is MIT licensed. All of the code that I talk about today will be MIT licensed, and it's available there on the GitHub repo if you'd like to check out the details. So it's a server that runs on Linux, and there's a cross-platform CLI tool. There's a web UI. And I'll just kind of point out that we have two different classes of client that interact with our server. One is the OS Query agents. So these are workstations, production servers that are checking in, retrieving configurations, sending the data that they've collected down to the server. And then we've got humans or scripts accessing more of the administration interface. I also want to mention that throughout this talk, I reference users and customers. In this case, for us, they're basically the same because as an open core product, our customers are also using the same code base that our users are using, only with some more features turned on, essentially. So for a little bit of background, our infrastructure includes the Fleet server, of course. So that's written in Go. It's serving HTTP requests, sometimes terminating TLS, as we'll see more about that later. We use MySQL 5.7.21 plus, doesn't matter so much, to store most of the application state. And we also use Redis for caching and somewhat notably also for the pub sub queue. And part of the reason why our dependencies look like this and we try to get multiple uses out of each dependency is that people self-host our software and we want to keep this deployment simple. So this is what that looks like to some extent. It's fairly standard web app deployment. So you've got Fleet servers. This is where Go is, of course. Sitting behind a load balancer, talking to MySQL and Redis. And we've got our two different types of clients. And like I said, it's entirely self-hosted. We don't have a SaaS. And so we don't have access to the environments that our users and customers deploy the server in. This was a big motivator for some of the work that we did here to make it easier to do this kind of debugging. But I think that this strategy also applies to places where you do have more direct access to your services running in production. The environments that we deal with are also fairly heterogeneous. It's probably about 80% AWS. A lot of those deployments use some reference Terraform that we provide, and we try to, as much as possible, encourage people to kind of keep things consistent. But we just don't have that control. The other 20% is probably GCP, Azure, or in actual physical data centers. And when we think about scaling problems, we think about these two classes of API clients. So again, the agents, these are making requests constantly when they're online. About 10 requests per minute per host could be a normal workload, although it depends on how things are configured. And then there's the admin clients. So this is a human using the graphical interface on a web browser. This is someone using the fleet control command line tool, or this is someone who's written a script and maybe that script is running to access those interfaces. And so if you do a little bit of napkin math, you find that 100,000 host deployment, you end up with about 17,000 requests per second on the server. So we're not talking Google scale, but it's nothing to sneeze at. And what really motivated us is we wanted to find ways to resolve problems in the server quicker, because after all, people are using our server to do their work and they need to get back to work. Plus, we have features that we want to develop and we want to get back to work as an engineering team as well. So we're talking performance issues and we're also talking bugs in the functionality. And I also wanted to make sure it was possible that we could dig into the root cause of what was going on, even if we did something drastic like, as commonly works, why don't you just restart the server and see if anything starts working then? We can still maintain some of this state to go back and understand what may have been going on. And we also wanted to make the process really simple for our users, because our users end up having to operate a piece of software that they're not necessarily very familiar with. So looking into the tools that Go provides, there's runtime/pprof in the standard library. It includes profiles like Go routine, so you get the stack traces of every Go routine that's running. Thread create, you find out about the underlying OS threads. Block, you see which threads are blocked and why. Mutexes, allocations, both allocations over time on the heap and currently live objects on the heap, if you're interested in looking at memory, and CPU profiles. And I just want to say a huge thank you to people who on the Go team who've worked on these tools. These are some of the best tools that I've ever worked with in any ecosystem. And again, this is something that brings me back to using Go every time. So at the most basic level, using these things in the standard library looks something a bit like this. Open a file, and then call that pprof function to write the heap profile to the file. Now, I wouldn't necessarily recommend doing just exactly this. For most folks, I would recommend going to the net HTTP pprof package. And what this package does, still standard library, is it packages the profiling tools up into HTTP handlers. So the standard HTTP interface, as we just saw in one of the lightning talks, someone wrote with your response writer and everything like that. And when you import that package, it automatically attaches those handlers to your default http.servmux. It's way easier to explore the options when you have them like this than kind of digging through those Go docs. But also note, this is unauthenticated. So if you attach this to your default routes and you have a server that's listening on the internet, well, now anyone who can hit that server can get all this debug information. So be careful where you expose it. You could expose it on a port that's not forwarded. You could expose it on an interface that's not available. Few options there. And essentially, this is all that looks like. You really just need to import the package, start up a server, and run it. So if you already have a server running and you're using that default servmux, the routes will be right there. If you're not using the default servmux, you just import the handlers from that package and attach them to whatever mux you're using for that. And you can put them at any URL routes that you want. And so a recommendation to everyone who's new to this is use the index that's provided by the net HTTP pprof to see the types of profiles that are available. This is what that index looks like. And you can actually click to generate any of these profiles. You get some descriptions of what the profiles look like. And depending on which profile it is, it'll either open right in your browser because it's a text file, or it's more of a binary file and you'll get a download Once you've got the file, then you'll want to use GoToolProf to analyze the collected profiles. That's not true for everything. Some of these things are plain text, but GoToolProf interprets a number of these profiles. There's a really useful browser UI for exploring the actual collected profile. I highly recommend using this. So this is another recommendation. Use that GoToolProf-HTTP command to view the profiles that you generate. And this is what you end up seeing. You've seen some of things like this in the lightning talks. You don't need to worry too much about the details of this, but I just want to show you that these things are there. Flame graphs. This is cool. If you'd like to learn more about this, there's actually a talk coming up this weekend. Tomorrow, Zach Musgrave is talking about real-world profiling in a database that they built. That is tomorrow at 1:50, and I believe the next room over. And if you can't even wait until tomorrow, there's some awesome talks from 2019 that you can check out to go much deeper into using these profiling tools. Dave Cheney from GopherCon in 2019 and Alexander Else from GopherCon Australia in 2019. Highly recommend checking out these talks and becoming more familiar with these tools. I think as you'll see as we go through this, even just have a cursory understanding of these tools can really pay off a lot of benefits when looking at what they can provide us. So we looked at what was there in the standard library. It's awesome. It's really useful. But we had some requirements that were not met directly by what was in the standard library. We wanted a process that we could go through with our users, with our customers, that was easy to use, and meaning we can get even relatively non-technical users to do it, because the folks using our software are often IT people or security people. They're not software engineers, and they're not DevOps engineers. And so asking them to log into servers and run tooling is not necessarily always a trivial thing for them to do. We also wanted to minimize the round trips. This, we think, is super important for quicker resolution of problems. And I think this applies no matter whether you're working with people outside your organization or people in the organization. And lastly, we wanted to be sure that it was authenticated. So like I said, the standard net HTTP pprof connects everything on the default servmux, and you're likely exposing all of that information to the internet or to the entire network where the server is accessible. So to make this easy to use, we wanted to avoid installing additional tools on the user's system. Our users already have the fleet control command line tool installed. And so we saw this as an opportunity to build the functionality into that so that if they were using Fleet, they would already have the tools that they needed to debug Fleet and provide us the information that we need to help resolve their problems. We also wanted to create a single artifact so that it's as simple as, please just give us the file that's generated by this command. So we just package it all up into a tar.gz. It's easy to move it between computers. Round trips, of course, take time and energy, coordination, effort between people on both sides, for us, between our customers and folks in our organization. But again, like I said, this could be between engineers on your team and the operations folks who run the servers. This could be a matter of logging into servers and getting the credentials to do those kind of things. And so the idea that we came up with was, why don't we just collect everything that we think could be useful, and we'll do the analysis on those things later. And what this also means is that you can use these kind of crude techniques for remediation, such as try restarting the server. Does it work now? We've all seen that work with software. So as a recommendation, I would say to folks, collect more up front. You're not likely going to pay a very high cost to collect this information, but it could really pay dividends. And for authentication, there's potentially sensitive information in these profiles. In fact, one of the profiles that's provided is, or it's called a profile, but I wouldn't necessarily say it's a profile, but Prof provides the ability to get the command line of the running program. There might be secrets in there, for example. So we wanted to make sure that there was authentication to access these things. And of course, as a web application, we already had authentication, and our fleet control command line tool already knew how to authenticate with that application. So we just piggybacked on the command line tool. So recommendation, of course, control access to these endpoints. And this is a sort of simplified example of what controlling that kind of access could look like. So in this case, we're using the Gorilla Mux router. We attach the handler functions, which are just the command line and profile functions that come from the net HTTP pprof. And again, this is where Go is really cool. Like, we've got this standard interface for what a handler looks like. It doesn't matter which routing library we're using. We can attach these handlers and get the benefits of this. And so then adding the middleware for us was simply a matter of calling this use method on the Gorilla Mux router to add the middleware. And we're not covering it here, but of course that middleware is going to be validating some sort of authentication token that the user has. So what does this all look like in practice? And I'll note, I'm about to show this. There's already been a login performed in the background as you see this. So we run the fleet control debug archive command. It runs a bunch of profiles immediately, and it actually looks like it's hanging a bit here, but what's really happening is it's running the CPU profile, where it's taking samples of where the program execution is over time. So this was actually sped up 2x. I think it waited 15 seconds there. Normally it would wait 30 seconds by default while it's taking that profile. And I'd also note that there are some other things that were not included in net HTTP pprof that you'd also see generated in there, the DB locks, the InnoDB status, and we'll talk more about those in a bit. We print a warning to the user to be kind of careful about where they're sharing this, but this is also something that we've really considered in terms of what is the debugging value of any information that we're collecting versus what is the potential sensitive nature, are we getting credentials, that kind of thing. And it's collected up all into that tar archive, and we would just ask the user to send that up to us. If you untar it, you'll see all the profiles are there. Some of them are in that pprof format, some of them are in JSON. And we can look at how this actually worked in a real world scenario. So we had a real report from a user on our Slack who said, our fleet servers are pegged at 100% CPU. We can't figure out why. We're seeing these errors in the logs. TLS handshake error, EOF, like tons of these errors in the logs. And the first thing that we said is, can you please create one of these debug archives? I'll digress here to say, it's really important to know what normal looks like for your system. So let's take a look at normal for our system. This is a flame graph, and there's lots of words there. You don't need to look at the details totally. And we'll see why in a moment. We heard them say they were having CPU utilization issues, and so we said, well, let's look at the CPU profile. I've found the flame graph to be a helpful way to look at these kind of representations. So here's normal. Here's what we got from the user. And even knowing nothing about this and probably not being able to read the text on here, you can see the structure of these graphs is really different. So I'll just flip back and forth. Really different structure here. And when we looked at this, what we saw was, we're back to the normal graph here. So under normal conditions, our TLS termination takes up maybe 10% of the CPU cycles, and the business logic, which I've highlighted in blue up there, takes up about 80%. This seems like a server doing mostly what we want it to be doing. Looking at what they provided us from the archive, again, the business logic is in blue, tiny fraction of what the server was doing. The TLS termination is in red. What is going on here? We're spending over 90% of our cycles in TLS termination. And again, this talk isn't about really digging into these profiles, but if you look down at the bottom thing that we can see on here, we see big.addMul VVW. And we go to our debugging friend Google, essentially, and we find this issue on the Go repo. And what we find is discussion of Go's RSA algorithms are dramatically less optimized than the ECDSA algorithms. And the suggestion on the issue is just generate a new certificate with ECDSA and see if things work better. So we suggest this to the user. We've figured this all out very quickly with no round trips to the user. But we are able to go back to the user and say, are you using an RSA certificate? Yes. Can you try generating a new ECDSA certificate? They try it, and it starts working as expected immediately. So I don't know the state of this issue today. It looks like there's been optimizations of RSA on some platforms, but this might be a pitfall to watch out for still in TLS termination in Go. And as a recommendation, what I just showed you was taking kind of a very intuitive look at those flame graphs. They had such obviously different structures that it was clear what was going wrong. It's not always going to be that clear, and Prof has some really cool tools for comparison where you can actually take a base profile and subtract a new profile from that, compare what changed. So if you're working on optimizations or you're working on figuring out what's going wrong under some specific circumstances, you can use that functionality to try to tease out the differences. And another recommendation is just make this kind of collection a standard part of the runbook. We have not always been the best at this, but in the scenario that I just described, we actually did reach for this tool first, and this led to a really quick resolution of the issue. We didn't have to have all these back and forths. And so even if you're talking about your own internal applications, it can really help to collect this kind of information, because maybe you restart the server and move on, but maybe this archive will turn up information that's useful to you and your investigation later. And we went beyond what was available in Prof. We started to ask ourselves, what is the information that we request of our users when they report issues? And we sort of created a rule of thumb. If we find ourselves asking for something more than once, and the cost of collecting it is reasonable, with reasonable being measured by the resource utilization of the server and the infrastructure dependencies and the size of the data that's generated, and maybe also the sensitivity of the data, then add it to this archive that's collected so that we have all of the information to work with. And a recommendation, if you're taking this kind of approach, identify what I'm calling here local state. So for example, the CPU or memory profile of the running process versus state that is the entire system, such as errors that are happening across multiple processes, infrastructure dependency statuses, these kind of things, and decide which local state and which system state you'd want to collect. So for us, errors became a very apparent one. Almost always a debugging step was, well, can you look at the logs and see if there are any errors in the logs? And for us, in our users, it's not always easy to search the logs. The logs are maybe even going to dev null. They're maybe being thrown out. Maybe they're going to an Elastic cluster and people don't have credentials for it. Maybe they're going somewhere in AWS. Our users just didn't always know. So we collect the errors. We treat this as system state. So we collect the errors across all of the different processes that are running, all the different fleet servers that are running behind the load balancer. We store those in Redis, and then we can pull them back out as part of that system state when we create the debug archive. So this is kind of a simplified version of the code for doing that. But essentially, we take the error, we marshal it to JSON, and then we hash that. I think it's like a SHA-256 hash. So we end up with just, and then we base 64 it. So we end up with some characters, a not very long string. And then we use that to generate keys in Redis where we store the full JSON. And this full JSON includes some additional metadata. I'll show you an example in a moment. And we also store the count across all of the different load balance fleet servers of this error. And we set them to expire as well so that we're not building these things up indefinitely. And then when it comes time to generate the debug archive, the fleet control tool reaches out to the server and says, well, what errors do you have? And here's, again, just a normal HTTP handler. Serve HTTP with a response writer and HTTP request. And essentially, all we do is retrieve the errors out of that store, marshal all of that up into JSON, and return it to the client. Here's what those errors look like, for example, and you can see some of the additional data we attach to this, like the stack trace of where it's occurring, and the count of how many times it's occurred. So imagine a scenario where someone comes to us and says, I'm trying to enroll my agents and they're not connecting. If we get a debug archive, we can look at it and see there were like 300,000 errors where there was no secret that matched when the enrollment happened. And we can go to them and say, it looks like you've probably misconfigured your agent. If instead maybe we're seeing errors that we can't connect to the database, we know that it's a completely different issue. And we also can identify errors that are actually like really uncommon. For example, this is one from a human actually interacting with the application. And this is an error that's probably not really very notable for us to look at unless we're debugging some sort of issue where a person says, well, I'm trying to create a query and I was unable to do so. We also look at the database, in our case, MySQL, because we commonly found that we were having performance problems that were related to how our application was using the database. And again, we looked at what are the commands and the outputs that we're asking for from our users to try to do this debugging. We found essentially it was often the process list, the database locks, and the InnoDB engine status. And so we said, well, let's include these things in the debug archive also. And what you see here is a function that takes essentially a function that generates debugging information and transforms it into an HTTP handler. So you can write a function like this, InnoDB status. We write this on our data store. There's a data store interface that we're using. And this is going to return that InnoDB status for MySQL. Well, the JSON handler turns this function into a function that we can connect, again, right onto our normal MUX, and then collect with the tooling that we've already built. And a recommendation that comes out of this is collect everything into one place. So not just the local state, not just the system state, but all of it. And I think that even if you're talking about your internal services, you still might have engineers that need to go to multiple different systems to see what would be going on. Maybe you've got graphs in Grafana and you've got logs somewhere else, and you have to put all of this together to understand. Well, maybe collecting it all into one place so that you have a central artifact that can be shared by the team doing this debugging could be a good approach to use. And for us, a wish list of kind of where we would like to go next with this functionality. We already have a debug tool for migrations. A common situation that we see is our users end up deploying a new server version but somehow don't run the database migrations. We'd like to include this information in the archives. Getting the full server configuration, because particularly if you build a server that can be configured through environment variables, through flags, through config files, there could be some mix of those, and users don't necessarily always know what they've done and what effective configuration they're running. It would be important with this kind of thing to be sure that we're redacting secrets, because you're going to have things like your database credentials in there almost certainly. And for us, Redis is an important infrastructure dependency that we don't really get any visibility into with this. Probably for us, it's because we haven't run into too many issues with Redis. Our use of it is relatively light compared to our use of MySQL. And then we've also got these Prometheus metrics being collected by the instance. And I think this could be super useful as well to understand what kind of utilization is this server seeing, what kind of response codes is it returning. Prometheus makes it really easy to gather these things, and so the server could sort of report on its own Prometheus metrics as part of this archive. And my recommendation to you all is, as you debug and as you discover new data sources that are useful in your debugging, iterate on the tooling that you build. The investment that you make in your tooling could pay dividends later when you're in an incident or when you learn something really important about your systems. So looking at doing it yourself, I'll wrap up by kind of reviewing the recommendations. So explore what's available there with the tools. Use the HTTP pprof index to start exploring these things. Learn what normal looks like for your systems so that you can have an intuition of what's going wrong when things are abnormal. Identify the local state that you're interested in versus the system state that's across your entire system or service. For collection, collect more up front, especially if the cost is low. Just collect it and you may find it useful someday. On the flip side, control who has access to that data. So make sure those endpoints are authenticated or not exposed on public interfaces. Make collection a standard part of the runbook. So don't forget to do this. It's easy to enter an incident and immediately start asking questions. It can make sense to collect the information first and then start asking questions once you've had a holistic collection of the useful information. And collect it all into one place, perhaps even if you have access to all of the internal systems that would provide the information that you need. And then analyze. So use the pprof-http tool to view the profiles. It's really, really awesome to be able to filter and move through different views to understand those profiles. Use the comparison tools as well, and in particular, if you identify performance problems and then you want to test whether you've made improvements, those comparison tools are very cool. And then iterate. Whatever you're doing, whatever you're finding useful, build it in so that instead of an engineer having to figure out the command to run, next time make it run automatically and collect that information. Always improving our tools is a great investment. And that's it. So thank you, everyone. You can find me on Twitter and on Gopher Slack. And we're also hiring at Fleet for an engineering manager working on C++ and Go, if you're interested in this stuff. Thanks.